In this video, let us discuss what is Poisson's bracket and some of their properties. To know what is Poisson's bracket, let us choose a function f. And this function f represents a dynamical variable of a system. And it is also a function of conjugate variables like position coordinate qj, momentum coordinate pj and time. So in equation form we can write f as a function of qj, pj and time. Let us take it as equation number 1. For this f, let us find the total time derivative of f. So total time derivative means df by dt. So using a chain rule, we can differentiate this f, which is the function of qj, pj and time. When we differentiate, we will get dou f by dou qj into dqj by dt plus summed over j dou f by dou pj into dpj by dt plus dou f by dou t into dt by dt. This dt by dt will get cancelled. We know in classical mechanics this dqj by dt can be, one time differentiation can be replaced by qj dot. So this equation can be written as summed over j dou f by dou qj into qj dot plus summed over j dou f by dou pj into pj dot plus dou f by dou t. Let us take this as equation number 2. We know from Hamilton's canonical equation of motion, the value of qj dot is equal to dou h by dou pj and pj dot is equal to minus dou h by dou qj. So let us take this as equation number 3 and substitute this equation number 3 in equation number 2 in place of qj dot and pj dot. When we substitute, we get df by dt as summed over j dou f by dou qj into dou h by dou pj minus summed over j dou f by dou pj into dou h by dou qj plus dou f by dou t. Now the first and second term put together, which is equal to dou f by dou qj into dou h by dou pj minus dou f by dou pj into dou h by dou qj can be written as f comma h. That is the Poisson's bracket of f comma h. So our equation becomes df by dt equal to f comma h, that is the Poisson's bracket of f comma h plus dou f by dou t, where this f comma h is called as the Poisson's bracket of f with Hamiltonian h. So this Poisson's bracket is almost equal to the commutation relations what we study in quantum mechanics. So in place of f and h, if we replace it by some other two dynamical variables x and y, then we can define the Poisson's bracket of x and y as summed over j dou x by dou qj into dou y by dou pj minus dou x by dou pj into dou y by dou qj. So this is the simple definition for a Poisson's bracket. So this is written in terms of x and y. We can use any other two dynamical variable to produce a Poisson's bracket of two dynamical variables. So our equation 4 now becomes df by dt is equal to Poisson's bracket of f with h plus dou f by dou t. If in case this function f is a constant of motion, then we can write this df by dt equal to 0. So our equation reduces to the Poisson's bracket of f comma h plus dou f by dou t equal to 0. And if this function f does not depend on time explicitly, then again our dou f by dou t is also vanishes or goes to 0. We get the commutation of f with h is equal to 0, that is or the Poisson's bracket of f with the Hamiltonian h goes to 0. So if a function f does not depend on time explicitly and is also a constant of motion, the Poisson's bracket of that function with the Hamiltonian vanishes. Or you can say A function whose Poisson's bracket with the Hamiltonian vanishes is a constant of motion. Next, we will discuss some of the properties of Poisson's bracket. The first important property is they are anti-commutative in nature. That means the Poisson's bracket of x comma y will give you minus of y comma x. This means this gives out the antisymmetrical property of the Poisson's bracket, or we can say this Poisson's bracket does not obey any commutative laws of algebra. And then the Poisson's bracket of a variable with the same variable will give you 0. That is, the Poisson's bracket of x with x, y with y, z with z will give you 0. The third property is the Poisson's bracket of any variable with a constant will give you 0. So x comma c is giving you a 0 where c is a constant. The fourth property, the Poisson's bracket of cx with y will give you c times the Poisson's bracket of x comma y. Again, c is a constant here. The fifth property is associative property. X, the Poisson's bracket of the variable x comma y plus z is equal to x comma y plus x comma z. And the sixth property is x comma y z. The Poisson's bracket of x comma y z will give you y into the Poisson's bracket of x comma z plus Poisson's bracket of x comma y into z. And dou by dou t of Poisson's bracket of x comma y will give you the Poisson's bracket of dou x by dou t into comma y plus the Poisson's bracket of x with dou y by dou t. And the eighth property is the Poisson's bracket of x with the Poisson's bracket of y comma z plus the Poisson's bracket of y with the Poisson's bracket of z comma x plus Poisson's bracket of z with the Poisson's bracket of x comma y will give you 0. This property is called as Jacobi's identity. Next, there are few properties of Poisson's bracket which are called as the fundamental properties or the special properties. The Poisson's bracket of Qi with the Qj, or the Poisson's bracket of Pi with the Pj, the Poisson's bracket of position coordinate of ith particle and the jth particle, or the momentum coordinate of the ith particle and the jth particle with it will give you 0. This is the first fundamental property of Poisson's bracket. The second one is the Poisson's bracket of Qi and Pj will give you delta ij, that is the Kronecker delta. So which means it will be equal to 0 if I is not equal to j, and will be equal to 1 if I is equal to j. So let us prove this fundamental properties. The first property, that is the Poisson's bracket of Qi with Qj. So expanding using the definition of Poisson bracket, so we get summed over j or summed over k. It is dou Qi by dou Qk into dou Qj by dou Pk minus dou Qi by dou Pk into dou Qj by dou Qk. So we know this Qi and Qj's are not the function of the momentum coordinate. So this dou Qj by dou Pk and dou Qi by dou Pk will give you 0. So substituting this 0 value in the above definition, we get Qi into Qj. The Poisson's bracket of the Qi with the Qj will give you 0. In the same way, we can prove the Poisson's bracket of the momentum coordinate of the ith particle with the jth particle will also give you a 0 value. So the next fundamental property is the Poisson's bracket of Qi with the Pj. By the definition, we can expand it summed over k, dou Qi by dou Qk into dou Pj by dou Pk minus dou Qi by dou Pk into dou Qj by dou Qk. So we know this Qi's are not the functions of Pk. So the second term will completely vanish. So we will get summed over k, dou qi by dou qk, dou pj by dou pk. So also we can write this dou qi by dou qk as or equal to delta ik, and this dou pj by dou pk is delta jk. We know these deltas are nothing but they are the Kronecker deltas. So substituting these values of dou qi by dou qk and dou pj by dou pk, we get this Poisson's bracket of qi into pj as delta ik into delta jk. So this can be simplified as delta ij. So this we know this Kronecker delta will be equal to 0 if I is not equal to j, and it will be equal to 1 if I is equal to j.